Hello everyone, in this video I'm going to analyze this beam using slope deflection method. So support A is fixed and we have two more supports B and C, which is roller support, and there is an UDL of 5 kilonewton per meter and a point load of 20 kilonewton. So here it is also mentioned that support B sinks. Okay, so this sinking is 15 mm. So this B support sinks. That means this will move 15 mm down. Okay. So here I can put delta is equal to 0.015 meter. So this 15 millimeter I converted to meter. Now we will be using slope deflection method to analyze this beam. So in this method, so we have to use the equation like if moment at AB is equal to moment of AB fixed, that is fixed moment, plus 2EI by L bracket 2 theta I plus theta B minus 3 delta by L. So this equation we'll be using. Now here we also need EI value. So coming to the E value, if I look at, E depends on the material. So if it is aluminium, so the E value will be for aluminium. If it is steel, and so here we consider it as steel. So let's take 210 GPa, and then we also have to take I. So now if we consider this as reinforced concrete RC beam, so for that the E value you have to do experiment, okay, because RC is composite of steel as well as concrete. The concrete E value is different from the steel. For concrete, if you are referring your code like IS code, it is like 5000 root over of FCK, so that will differ. So in this example I am going to consider for steel, and I value, which is the moment of inertia, so E is the Young's modulus, I is the moment of inertia. So let's take the cross section of steel as a rectangular of 50 mm width to 200 mm depth. So if it is a I or circular, you can refer steel table to get the I value, moment of inertia. So here for the rectangular it is BDQ by 12. So B is 50 multiplied by 200 Q by 12. So EI value, because if you look at here, it is we are using EI. So EI, I'm going to multiply 200 GPa with this. This unit is mm4. So if you are converting this to SI, kilonewton meter square, once you multiply with this, you will get 7000 kilonewton meter square. So I'll be using this value 7000. Now if you look at, sometimes you may have different dimension, okay, the I, that is throughout the beam, if the dimension is different, so the I will be different. Here where EI is constant because the material as well as the dimension is constant throughout the beam. So we are going to consider EI as 7000 here. Now let's calculate the MAB. So MAB is fixed moment. So as we have in AB span, we have 5 kilonewton meter UDL as well as a point load of 20. So calculating the fixed end moment, for 20 it is minus 20 W into 3 into 2 square by 5 square, because the fixed end moment for a point load will be W, which mentions the point load, A B square by L square. So here A is 3 meter, B is 2 meter, L is the total span, which is 3 meter, okay, which is 5 meter, 3 plus 2. So this plus we have for the UDL. So for this is for point load, fixed end moment, and for UDL you have the formula WL square by 12. So W is, so here we have to, again it is negative this side, minus at support A So minus 5 is the UDL. Then the span is again 5 square WL square by 12. Okay. So this is your fixed end moment. Then plus 2 EI by L. So 2 EI is 7,000 by span is 5, 2 theta A. So the slope at A, because it is a fixed end, it will be 0. Okay. So if you remember, if there is a fixed end, how the deflection will be? So here there is no deflection, right? So there is no slope here. Here theta is 0. So our theta A at support, it is equal to 0. Whereas at theta B, it is not equal to 0. We have slope at B. This is how the beam bends. So theta A is equal to 0. That's why first term is 0 plus theta B is unknown, which we will be calculating, minus 3 delta is given, which if the support does not sink, then we have to take this as 0. But we are solving for sinking support, or sometimes it can give us a settlement value. Okay, this can be a settlement. 3 into 0.05, 0.15 by 5. L is the span, because this span of AB is 3 plus 2, 5 meters. So L is equal to 5 meter for this AB span. So this implies our MAB is equal to, so this adds up to minus 9.6 minus 10.42 is the fixed end moment, plus 2 into 7,000 by 500 is 2,800. Theta B minus, this is 9 into 10 to the minus 3. So this gives minus 20.02 plus 2,800 theta B minus 25.2. So we can add this to. So finally I can write MAB is equal to 2,800 theta B, this term first, then minus, because minus 20.02 minus 25.2, so minus 45.22. So this comes as first equation for the moment AB. Similarly, we will be now calculating for MBA, then MBC and MCB moment. So MBA. So MBA, so here it will be like MBA fixed end moment plus 2 EI by L plus 2 theta B. In the previous case, it was 2 theta A plus theta B. So here it will be 2 theta B plus theta A minus 3 delta by L. Okay. So fixed end moment for this. So this side, it will be positive 20 W AB square by L square. Okay. Plus the UDL WL square by 12. Then plus 2 EI is 7,000 by span is against 5. Then 2 theta B plus theta A is 0 minus 3 delta by L. Same. So this gives us 24.82 plus 5,600 theta B minus 25.2. So we can write as MBA is equal to 5,600 theta B minus, because 24.82 minus 25.2, 0.38. This gives us second equation. Similarly, we will now calculate for span BC. So in span BC, it is 2 meter span and we have only UDL of 5. Okay. So we will calculate MBC, which is, so fixed end moment plus 2 EI by L. So 2 theta B plus theta C minus 3 delta by L. So fixed end moment is only 5 kilonewton per meter WL square. Here span is 3 by 12 plus 2 EI because EI is constant, so same 7000. Span is 3 meter. 2 theta B because this is unknown. Here theta C also will come into picture because this is not 0. And here if you look at the 3 delta by L where the delta is sinks, here in this case because we are taking, because sinking is at support B, right? So we are taking right side of this. So here we have to do positive. The sign will be positive here. 3 into delta by span 3 meter. Okay. So this gives minus 3.75 plus, if you multiply this, so it will be 9,333.33 theta B plus 466.67 theta C plus 70. So MBC is equal to, first let me take the theta B term, then the theta C term, then adding 70. Okay, this is plus 70. 70 minus 3.75 gives 66.25. So this gives our equation 3. Next is our MBC. So MCB, we calculated MBC. So we are calculating at point here MAB, then MBA and BC, then MCB. Okay. So here MCB is equal to plus WL square by 12. So 3 square by 12 plus 2 EI by L. So 2 into 7000 by 3. So here it will be 2 theta C plus theta B and plus 3 into 0.015 by 3. So MCB is equal to 466.67. When you solve this, you will get this value. Theta B plus 9,333.33 theta C plus 73.75. This gives 4 equations. So what unknowns we have? We have 6 unknowns now. MAB, MBA, MCB, and I'll write first MBC, then MCB. And also we have theta B, theta C, because theta A is 0, right? This was 0. So we have 6 unknowns. And now we have 4 equations, right? We need 6 equations. So what are the 2 extra equations so that we can solve this? So if you look at here in the beam, at moment C, you can see here this moment at CB, it will be equal to 0 because it's not fixed, it's roller support. So here the moment is 0. So we can put one equation as MCB is equal to 0. So this is equal to 0. So this is one equation. So I can write this here, 466.67 theta B plus 9,333.33 theta C is equal to, because, okay, let me just write this as plus 73.75 is equal to 0. Okay, because MCB is equal to 0. So this I can write, just taking this to the right side, this is equal to minus 73.75. So this gives me a equation number 5. Another equation, I can write MBA plus MBC is equal to 0. At this point B, because the summation of moment here, it should be equal to 0 at point B, right? So MBA and MBC is equal to 0. So adding this to equation MBA and BC, that means this equation 3 and equation 2. Okay, so 5600 theta B plus 9333.33 theta B. Okay, this is theta C plus 4666.67 theta C, then 66.25 minus 0.38. So this gives me 14933.33 theta B plus 4666.67 theta C is equal to minus 65.87. So this is equation 6. Now solving equation 5 and 6. So we have two equations, two unknown, which is theta B, theta C. So you can use your calculator to solve this two equation. So and this you will get theta B is equal to minus 2.301 into 10 to the minus 3, and theta C is equal to minus 6.751 into 10 to the minus 3. So once we get these two values, now we can calculate all the moments. From equation 1 to 4, we can calculate the moments. So I'm going to put this theta B and theta C values from equation 1 to 4. So MAB is equal to, if you look at MAB, so you can find out once you put the value of theta B. Similarly, MBA, once you put the value of theta B. And then your equation 3, MBC. And MCB is equal to 0, we know. So MAB, once we put this value theta B, theta C, you get 51.66 kilonewton meter. MBA minus 13.26 kilonewton meter. MBC is equal to plus 13.26 kilonewton meter. And we already know MCB is equal to 0. Okay, so we have calculated the moments by using slope deflection method of the beam. So let's also draw the shear force and bending moment diagram. Okay. Now coming to the bending moment diagram, so we have this A, B and C, right? The spans of the beam. And first what you have to do is, here these are the moments at the supports, right? This the moments we have calculated at the support. So first I'm going to draw the simply supported bending moment diagram. Okay. So as we know, it's our beam is, this is 5 kilonewton per meter UDL, and there is a point load of 20 kilonewton. Okay, so I'm going to divide this into two different beam because I'm going to calculate the simply supported bending moment diagram. So here that means this AB and BC. So here it is 5 kilonewton per meter, and there is a 20 kilonewton span, 3 meter and 2 meter, and this is 2 meter, only UDL of 5 kilonewton per meter. So simply supported means for this we can directly calculate WL square by 8, which is 5 into, this is 3 meter, okay, 3 meter span, 3 square by 8, which is 5.625 kilonewton meter. So this bending moment diagram for BC is 5.625. In this case, because there are two loads, one UDL and point load, so we have to calculate the reaction first. So I can just write like moment at B is equal to 0. So RA into 5 minus 5 into 5 square by 2 into 20 into 2 is equal to 0. So you get RAV is equal to 20.5. So this is 20.5. So total load minus 20.5. Total load is 20 plus 5 into 5. So you get 24.5. So I'm just solving the simply supported beam here. Okay. So the moment under the load I'm going to calculate, okay, where it is like 3 meter and 2 meter. Okay, this is 3 meter. So under the load, if I'm going to calculate, so this will be 20.5 under the load is 3 minus 5 into 3 square by 2 minus, okay, that's what. So this gives me the moment as 39. So let me do the bending moment diagram here. So this is little more. Okay. So here it is 39. Okay. This is simply supported bending moment diagram for both the spans. Under this, with this, I'm going to superpose this moment, support moment. Okay. So here the support moment is at MAB is minus 51.66, so somewhere like this, 51.66. This is negative, whereas this was positive. Now at B we have 13.26, so somewhere here I'll put, okay, 13.26, and then we have 0 here. Okay. So this is negative, this is negative, negative, and here it is positive. This is positive. So this is your bending moment diagram. For example, now if you want to calculate, let me just take at the mid section of here, you want to calculate for the beam, okay, for the whole beam. So that means here moment at mid span of BC, it will be positive, you can see plus 5.625, and negative of, you can see if this is 13.26 and this is 0, mid means you can use, if any other distance you can use triangle, law of triangle. So 13.26 by 2, because this is at mid span, so I will just write 13.26.2, because here the value is 13.26 by 2, okay, and here it is because 13.26, so it's a triangle. So at the support moment, that is negative moment at the midspan of BC will be 13.26 by 2. So this gives me almost minus 1 kilonewton meter. So this is the final moment if we look at the whole beam for the section XX. Okay. So like this, at any section you can calculate the moment, any point of this beam, by subtracting the support moment with the simply supported moment. Okay. So this is the bending moment diagram where we superpose the simply supported and the support moment. And simply supported moment is the positive one and support moment is the negative one. Now coming to the shear force diagram. Okay. So again similarly I am going to divide both the span. So there is an UDL and a point load, and in this only UDL. So I am going to put this as RA reaction, RB dash, and here RB double dash. Here I am going to put RC. Okay. Now I am going to write down the moments that we have calculated here. So MAB minus 51.66. So this is 51.66. And then we have minus 13.26. And here plus 13.26. So I'm going to, if you look at the sagging, which we take as like positive bending moment, so this is negative and this is positive, or we can say right clockwise as positive. That means that from here if you look at, this is clockwise, this is positive, and this is because anti-clockwise it's negative. For shear force we always take this as positive sign convention. That means upward positive and here downward. From right side, if it is downward, then it is positive. So calculating the reaction RA, I can write RA multiplied by, because this is 5 meter span, this is 3 meters, so 5 minus this is 51.66 minus there is a load which is at a distance of 2 meter from B, so multiplied by 2 minus UDL 5 into 5 by 2 minus 13.26 which is at the B, the moment at B is equal to 0. So we get RA is equal to 33.482 kilonewton. So this is the reaction at A. So coming to RB dash, so for that span we can calculate total load is 20 plus the UDL 5 into 5 minus RA if I do, I am getting 11.518 kilonewton. Okay. Now coming to the span BC, either I can go with RB dash multiplied by this. So RB double dash multiplied by 3 plus 13.26 minus 5 into 3 into 3 by 2 is equal to 0 because moment here is 0. So this gives me RB double dash is equal to 3.08 kilonewton. Or we can also calculate like RC into 3 opposite direction, okay, minus the UDL 5 into 3 into 3 by 2 minus 13.26 is equal to 0. This will give you RC is equal to 11.92. So if you add this two, you will get 15 kilonewton, which is total load 5 into 3, right? So it is correct. Now let's draw the shear force diagram. So we have, again I'll draw this span. So let me just put this as A point, this is B point, this is C point. So at A we have reaction at A which is 33.482. So here positive. Similarly at RC, let's start from here, it is 11.92, I'll take here 11.92. Okay. And at B dash and B, you can see RB dash is 3.08, RB double dash, and this is 11.518. So RB double dash is this, okay, this is 3.08, so I can draw like this, and RB double dash, so I'll take this for the next span. So this is slightly smaller than 11.92, so I'll take this as 11.518 this. Now if you look at in AB span, we can still have, because there is an extra 20 kilonewton with the UDL, so at distance here which is 3 meter from here 2 meter where the 20 kilonewton is there, here the shear force will be like 33.482 RA, so minus 5 into 3 the UDL at that point, which gives for 18.482. So here we have, so let me just increase this line. So here we have 18.482. Okay. Then this shear force 18.482 minus the 20 kilonewton force, so this gives you minus 1.518. So here we have a 1.518. It's better to increase slightly. Just okay. So this is our shear force diagram for the beam. So we have analyzed the beam using slope deflection method, and we have also drawn the shear force and bending moment diagram. And this beam here, this beam is with the sinking support. which we have analyzed. Hope this video is useful for you. Thank you for watching.